Let's take a look at this one. The thing that makes this one improper is that as if we put a 0 into the denominator, then we would get a 0 on bottom, which is undefined. So anytime our integral is undefined in our interval, then that's an improper integral. So what we have to do is we have to replace that limit end with a, or that end of our interval with a letter, and we're going to take the limit as that particular value approaches, in this case, 0 from the right side. So let's rewrite this. Integral from a to 64 of x to the negative 1/2 power. So if we integrate that, we get x to the 1 greater power over that power, so over 1/2 or times 2. We're going to evaluate that from a to 64, and then we're going to take the limit as a approaches 0. So if we substitute in a 64, we get 2 times, that's the square root of 64. And then if we substitute in an a, we get 2 times the square root of a. And then we need to take the limit of that as a approaches 0. So if we take the limit, well, the square root of 64 is 8. 2 times 8 is 16. If we let a go to 0, then that term is 0, so we get 16. So this is an improper interval, and this one converges. As a gets closer and closer to 0, then our answer, which is our area, gets closer and closer to 16. All right, let's take a look at this one. This one is improper because our lower limit is going to negative infinity. So again, we're going to replace that bottom end with the letter A. Normally, if it's the lower limit, we put an A in. If it's the upper limit, we use a B. So we're letting the lower limit go to negative infinity. And we're calling that lower limit A. And then we're integrating e to the 10x dx. So this is just e to the u du. So if u is 10x, then du would be 10 dx. So 10 there, 1 over 10 there. So when we integrate e to the u times du, we just get e to the u. We're evaluating that from a to 0, and we're letting a go towards negative infinity. So if we put a 0 in, got 1/10 e to the 10 times 0, which is 0, minus 1/10 e to the 10 times a, or 10a. So let's think about what this limit is. For the first term, that's a constant. The limit of any constant is that value. E to the 0 is 1, so that's 1/10. Now the question is, what is that? Well, if a goes to negative infinity, then our exponent goes to negative infinity. If it's going to negative infinity, a negative exponent tells us that we can put that in the denominator and make the exponent positive. So our numerator is 1, and our denominator is getting closer and closer and closer to infinity. And if the denominator goes to infinity, that term goes to 0. So if that goes to 0, then we converge. Our integral converges. All right, if we take a look at the next one, again, because of the negative infinity, we are improper. So we're going to rewrite this. And we could integrate this by parts. And I would be prepared to do an integral similar to this on the test by integrating by parts. But since that's not the emphasis, let's use the table for this one. So flip through the table and we try to find an integral involving an e to the x and then power out front, or a function out front. So the integral of u e to the u du, the integral of u e to the u du is u minus 1 times e to the u plus c. So our u, that's the exponent, is negative 7x, which makes du negative 7 dx. So if this is going to be, if we're going to make this work, this first part has to be u, so we need a negative 7 to go with that x. So we need to put a negative 7 on bottom out front. And then that has the same exponent. Notice that's u, that's u. And then to get our du, we also need a negative 7 to go with the dx. So if we put a negative 7 there, we have to put another negative 7 on bottom. And don't forget, we're taking the limit of that. So we end up with a limit is a goes to negative infinity of 1 over 49, and this is just u e to the u du, and we said that integrates into u minus 1 times e to the u, and instead of plus c, this is a definite integral, so we're evaluating that from a to 0. So to evaluate that, we need to plug in 0 and a. So if we plug in a 0, negative 7 times 0 is 0, minus 1. Negative 7 times 0 is 0, so we get that there. And then for the next parenthesis, everywhere we have an x, we're going to put in an a. So the first term is not so bad. That's 1, that's negative 1, so we have 1 times negative 1 times 1 over 49, so that's negative 1 over 49. The second one, there's several different things we could do there. But the key thing is we're letting a go to negative infinity. The limit of that is a goes to negative infinity. So for that first term, the limit of that constant is just negative 1 over 49. The question is, what is the limit of that going to be? Is that going to converge or is that going to diverge? Well, let's look at that. Back. Let's look at the limit as a approaches negative infinity. Let's rewrite that a little bit. Let's call that 1/49. Uh-oh, I hit a button with my hand. In fact, let's pull the 1/49 in front. We can do that. And then let's call that minus 7a minus 1 over e to the 7a. So if we let a go to negative infinity, we're going to have negative 7 times negative infinity. So negative times negative will make that a positive infinity there. If we put a negative infinity on bottom, we're going to get e to the negative infinity, or we could bring that up and call that e to the positive infinity, which is also infinity. Infinity times infinity is just infinity, because they're both positive. So we have 1 over 49 out front, and that goes to infinity. In that, basically negative 149 minus infinity, that's going to diverge. That's going towards negative infinity. If either limit gives us infinity and not just a number, then we are going to diverge there. Okay, let's take a look at this one. Okay, let's take a look at this one. If we were trying to look this up in the table, we're not going to find anything that fits this very well. This does look like a u squared and an a squared. But if we do that, then the top would be u to the third. So we don't really have a good one that fits that. So there are different ways we can go about doing this. So one of these involves doing a trig substitution. So if this is u squared and a squared, then u is here, a is here, and then the square root of u squared plus a squared is there, where we call this theta. If you think about this, Pythagorean theorem, that side squared would be 3, the other side squared would be x squared, and that equals the hypotenuse squared. Well, if we square the hypotenuse, yes, that's right. So that general triangle that we've talked about in that substitution section, if we have a u squared plus a squared there, if u is there, a is there, then the square root of u squared plus a squared is there. So we can use this to determine our substitutions. So what is x going to be? X over root 3 is tangent from theta, which means x is root 3 tangent theta. So dx is root 3 secant squared theta d theta. We also need an expression for x squared plus 3 squared. So we need to involve the hypotenuse. And we don't want to involve another variable if possible. So if we do the hypotenuse over the square root of 3, and I just put the hypotenuse on top, so that will be easy to solve for, we have hypotenuse over adjacent. Well, adjacent over hypotenuse is cosine, so the reciprocal of cosine, remember, is secant. So that means that the radical is root 3 times secant. Well, that's the square root of x squared plus 3. We need x squared plus 3 to the second power. Well, if we have a square root and we want to turn it into a square instead of a square root, we can raise it to the fourth power. Think about if we have something to the square root, or the 1/2 power. If we raise that to the fourth power, when we multiply those exponents, we would get 2. So this is going to make x squared plus 3 to the second power. If we square the left, we have, or I'm sorry, if we raise the left to the fourth power, then this whole thing gets raised to the fourth power. Since we have a product, we can do that to the fourth power and that to the fourth power. And that's going to give us 9 secant to the fourth theta. So now we can make our substitutions. So I'm going to leave the values, the um, limits off of our integral to begin with. And then when we get through, we're going to have to come back and do the limit as, if it's the upper limit, we're going to call that b. So the limit as b goes to infinity of the alpha. So whatever we get for our integral. So x is root 3 times tangent. That's cubed, so cube and cube. The denominator is 9 secant to the 4th theta. And then dx is square root of 3 secant squared theta d theta. So we can do some reducing. Notice that's root 3 to the 3rd, and that's another one, so that would be root 3 to the 4th. Well, root 3 to the 4th is where we got 9. So the root 3 to the 4th and 9 cancel. Secant squared will cancel 2 of those. So that'll give us tangent cubed over secant squared d theta. Now, if the secant squared were on top, then tangent could be u, because the derivative of tangent is secant squared. But the secant squared is not on top. The secant squared is on bottom. So there are different things we could do here. We could keep a tangent out and then convert the other tangents into secants and do some dividing. Or if you're more comfortable working with sines and cosines, we could convert it to sines and cosines and see what happens. Tangent is sine over cosine. So tangent cubed would be sine cubed over cosine cubed. Secant squared is, or secant is 1 over cosine. 1 over cosine. So instead of dividing by 1 over cosine, let's multiply by cosine over 1. And that's not just cosine, but cosine squared, because it's secant squared. So that cosine squared will cancel 2 of those, leaving us a cosine on bottom. So we've got the integral of sine cubed theta cosine theta d theta. And again, there's more than one way we could do this. Again, we could have pulled a tangent over here and then turned tangent squared into secant squareds using an identity. But we're just doing it with sines and cosines, and essentially going to end up doing the same thing. We're going to pull a sine over, and that leaves us a sine squared. And the reason we do that is because we have a relationship between sine squared and cosine squared. Sine squared is 1 minus cosine squared. So in place of sine squared, we're going to put 1 minus cosine squared. That's over cosine, and we still have our sine out here. So now we can divide each of those by cosine. We can do 1 over cosine. 1 over cosine is secant, or we could just call it 1 over cosine. And then cosine squared over cosine is going to make cosine times sine. So just to make this a little bit, let's see how we want to do this. Cosine is going to be our u. Cosine theta is going to be u, which means du is minus sine theta d theta. So if we replace If we put a negative there to go with sine, we need to put a negative out front. So that gives us 1 over u minus u du. Or we could call that the integral of 1 over u du, also known as du over u, minus the integral of u du. So 1 over u du minus u du. So du over u is natural log absolute value of u. U integrates into u squared over 2. Our u is cosine. We could distribute the negative, so this is going to be a positive u squared, so cosine squared over 2, or 1/2 times it, minus natural log absolute value of cosine. So looks like, oh, yay, we've got it integrated, we're done. But remember, our original variable is not theta, it's x. So we have to go back and substitute. So what is cosine? Cosine is adjacent over hypotenuse. So cosine is root 3 over the square root of x squared plus 3. Well, cosine squared will just be that fraction squared. And when you square a fraction, you square the top and you square the bottom. Cosine is root 3 over root x squared plus 3. When I looked at the way they wrote this, they simplified that a little bit using properties of logarithms. We can pull out the 1/2 power, and we can call this 3 x squared plus 3 to the 1/2 power. And when we have log of something to a power, we can bring that 1/2 out front. And call it this. Now let's remind ourselves, what is our x approaching? Our x is going to be going towards infinity. So do we want to leave it like this or not? If this goes to infinity, then the denominator goes, or if the denominator goes to infinity, this goes to 0, and we don't know how to evaluate log of 0. So you might say, well, how can we fix that? Several different ways. The easiest thing would just be to split that log up. If we have a quotient, we take log of the numerator minus log of the denominator. And we can drop the absolute value bars because the absolute value of 3 is 3. The denominator is always going to be positive, so no need for absolute value there. If we want to, we could pull the 1/2 out front, whatever. So that's our integral. So we're taking the limit as b approaches positive infinity of this function. In this function, we're evaluating, where did we start at? Was it at 0? At 6. This function starts at 6 and goes to infinity. So we're evaluating this from 6 to, technically from 6 to b, and then b is going to infinity. So I'm not gonna, let's see. If we put a b in, we get 3 over b squared plus 3 minus 1/2 times natural log of 3 minus natural log of b squared plus 3. And then if we put a 6 in, we get 1/2 times 3 over 39 minus 1/2 natural log 3 minus natural log of 39. So put a b in and put a 6 in. So we're just looking for, is this converging or diverging? Well, all of that is going to converge there, of course, because all that is a constant. But as b goes to infinity, notice this fraction goes to 0. The denominator goes to infinity, so that fraction goes to 0, so that's gone. As b goes to infinity, that goes to infinity. If we distribute our negative, we're going to have a minus 1/2 natural log 3 minus a negative makes that positive, and that's going towards infinity. Then we have minus some constant that we get from here. So since this piece here goes to infinity, the constants are not really significant. Infinity minus something, infinity plus something is still infinity. So that goes to infinity, therefore this one diverges. So that one was messy because we had a messy integral to evaluate there. All right, let's do one more. That's all we have. So let's take a look at this one. If we take a look at this one, why is this improper, or is it? If we look at the function, notice x can't be 1. Well, 1 is right inside the interval that goes from 0 to 2, which presents a problem. So we can't integrate all the way from 0 to 2 because we have a discontinuity inside that interval. So what we have to do is we have to go from 0 close to 1. We're going to approach x. We're going to let c approach 1 from the left side, and we're going to do this integral. And then we're going to take the limit, and we're going to let c approach 1 from the right side, and we're going to go from c to 2. So notice in both cases, we're going to 1. So we're going from 0 to 1, and then we're going from 1 to 2. 0 to 1 and 1 to 2. We're just not quite making it all the way to 1. So let's evaluate what the integral needs to be. What is the integral of 8 over the cube root of x minus 1 dx? So we could rewrite that as 8 times the integral of x minus 1 to the negative 1/3. It's a cube root, so 1/3 is in the denominator, so if we move it up, it's negative. So u can be just x minus 1, so we have u to a power. Du is just the derivative of that, which is just 1 dx. So we don't have to pick up any constants or anything. We have our du. So to integrate that, we have u to the 1 bigger power, well, negative 1/3 plus 1, or plus 3/3, is 2/3 over that power. So instead of dividing by 2/3, multiply by 3/2. So we get 12 times u to the 2/3, which we could call the cube root of x minus 1 squared. And of course, we could put the square on the inside or the outside. Power and root. So 12 times the cube root of x minus 1 squared. So for the first one, we're evaluating that from 0 to c and letting c approach 1 from the left. And then for the other one, we're letting c approach 1 from the right. It's the same function, so the same integral. This time we're going from c to 2. So for the first one, if we plug in a c, we get 12 times the cube root of c minus 1 squared. And then if we plug in a 0, we get 12 times, if we plug a 0 in there, 0 minus 1 is negative 1. The cube root of negative 1 is negative 1, and then negative 1 squared is 1. When we take the limit of that, if we let 1 approach, or if we let c approach 1, if c is getting close to 1, 1 minus 1 is 0. Cube root of 0 is 0, so that whole first thing goes to 0. And then we have our minus 12. For our other one, we're going to take the limit as c approaches 1 from the other side. We're going to put a 2 in. So 2 minus 1 is 1. That's squared. And then we're going to put a c in. Okay, so the cube root of 1 squared, that's 1 times 12. When we take the limit of a constant, we still get 12 there. For this part, if c approaches 1, we get the cube root of 0, so all of that goes to 0. So we end up with negative 12 plus 12, so this one converges. We're not going to an infinity, we're just going to converge on this one.